In this video, we're going to talk about section 9.1 in our book Power Series. And this is the first of two videos on this. So we begin here the part of BC calculus that's referred to as the C part. It's on series. So we're going to lay groundwork here and get kind of a foundation, talk about what we mean by series and talk about geometric series, and then we'll use that to build other series. So an infinite series is an expression of the form a1 plus a2 plus dot 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 on and on. You can write it in summation notation. We'll do a lot of stuff in this chapter on using summation notations, so we want to make sure that we get very comfortable with those. Each of the individual numbers that are being added together are called terms, and the nth one is called the nth term. The partial sums of a series, of an infinite series, form a sequence in their own right. So if you start with a sub 1, the first term, and then a sub 1 plus a sub 2, the sum of the first two terms, and then a sub 1 plus a sub 2 plus a sub 3, and so on, each of those numbers will in turn form a sequence. So that will be then just a sequence of numbers, a pattern of numbers like we've seen before this section, before we started adding them. Now, if the sequence of partial sums has a limit, then as n goes to infinity, then we say the series converges to that sum s. And we can write that in summation notation as the sum I equals 1 to infinity of a sub I equals s. If the series does not converge, then it diverges. So it's an either-or distinction. A series is going to either converge or diverge. There's no other options. So let me see if I can slide this up a little bit. It's not cooperating. Okay, here we go. So here's our first example. Does 1 minus 1 plus 1 minus 1 on and on forever converge? Now, it's easy with infinite series. You can talk yourself into some trouble here. So you could think of maybe grouping these and say, well, you're going to have 1 minus 1, and then you're going to get the next 1 minus 1, and you're going to keep pairing these up forever, and you can say, oh yeah, it's going to converge to 0. Sadly, that is not correct. So you have to be very careful about any kind of groupings you do here. Now, instead, when there's any doubt, we always go back to our definition, which is about these partial sums. So remember, s sub 1, the first partial sum is 1. S sub 2, the sum of the first two numbers, is going to be 0. S sub 3, the sum of the first three numbers, is going to be back to 1. And S sub 4, I think you can see where we're going with this, is going to be back to 0. So if you write this sequence out, we have 1, 0, 1, 0, and on and on and on forever. And as we've talked about before, that is not getting closer and closer to a single number. So since it doesn't converge to a single number, it diverges. And if our sequence of partial sums diverges, then our series diverges. So the answer is no, it does not converge. Okay? Now, here's kind of an interesting one. So I'm going to write these as decimals because I think it becomes more clear. So this is 0.3, and this is 0.03, and this is 0.003, and on and on and on. So here, when you look at that sequence of partial sums, the first partial sum is 0.3. The second one, which is going to be 0.3 plus 0.03, is going to be 0.33. And the third partial sum, which is going to be sum of those first three terms, is going to be 0.333. And I think you can see where we're going here. This is going to get closer and closer and closer to 0.3 repeating, which we know is 1/3. So the answer is, does it converge? Yes, it converges to 1/3. Okay? Now, this is an interesting idea here. We're going to have to talk about a little bit. So an easy way to identify some divergent series. So this is a way of identifying some divergent series. It does not find any convergent series. So if the sum of a sub I, a sub 1 plus a sub 2, blah, 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 converges, then we know that these terms must be getting smaller. Right? Think about your limit of partial sums. As you add more and more terms, it's got to be closing in on some single number. So what we're adding each time must be getting smaller and smaller. So this has the form of an if-then statement. So if this is true, this is the condition or the hypothesis, then this follows. So an if-then statement is true if every time the hypothesis is satisfied, the condition must also follow. Now, logistically, the converse is not true. So if you say, if the limit as n goes to infinity of a sub n equals 0, then the series converges, that is not true. So and that's a common misconception. That is not true. So I like to say, my favorite if-then statement, if you pay Mr. Street $1 million, then you will get an A in your math class. That is a true statement. Because, I'm here to tell you, every time somebody has given me $1 million, they have gotten an A in my math class, without exception. Now, the converse is not true. If you got an A in my math class, then you gave Mr. Street $1 million. Sadly, some people have gotten A's, and I've still not gotten my first $1 million. So you can see the converse is not true. Logistically, it can be true in one direction, but not necessarily true in the other. Now, the contrapositive logistically is true. Now let me back up a little bit. So we have converses where we switch the if and then. I just forgot what it is. So an inverse, that's what it is. So an inverse is where you negate the if and the then part. So you would say, if you did not pay Mr. Street $1 million, then you did not get an A in math class. That has the same logistic equivalence of the converse. A converse and the negation are either going to both be true or both be false. Now, when you negate it and switch the order, that is called the contrapositive. So in the example that I'm using here, if you did not get an A in my math class, then you did not give Mr. Street $1 million. That is the same truth that the original statement, if you gave Mr. Street $1 million, then you will get an A in math class. Okay, those have the same truth value. So if one of those statements is true, then so is the other. So a statement, an if-then statement, and its contrapositive are logistically equivalent. So we use that in this statement right here. So if we switch the order and negate it, it says if the limit as n goes to infinity of the individual terms is not 0, then the series cannot converge, therefore it diverges. That is known as the Nth Term Test, and we will use this many times. So this is one to kind of salt away. That's an important one. So for example, if we look at this series, 1/2 plus 2/3 plus 3/4 plus blah, 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 and we're given the nth term, and then it goes on and on and on. So does that converge? Well, if we look at that nth term, which we're actually given a formula for, and if we take that limit as n goes to infinity of that nth term, that is, we're taking the limit as n goes to infinity of n over n plus 1, as n gets really, really big, that plus 1 is insignificant. It's going to act like n over n, which is 1. because the limit is not 0, then we know the series must diverge. Okay? Now, it gets a little more complicated. So now we're looking at this summation of n factorial over 2n factorial plus 3. Now let's make sure we know what these n factorials are. So 5 factorial means 5 times 4 times 3 times 2 times 1. So n factorial means n times n minus 1 times n minus 2, all the way. You just keep doing this until eventually you're going to get to 3 times 2 times 1. Okay, so these get really big really fast. So we're going to find out eventually that this is a new king of the hill. In AP Calculus, we say that the fastest growing function is an exponential, but we will find out down the road that actually a factorial will outpace even an exponential, but that will come down the road. So the idea is we're looking at the nth term test here. So we're going to say, what is the limit as n goes to infinity, and this expression is our nth term. So that's n factorial over 2n factorial plus 3. Well, as n gets bigger and bigger, these factorials are just blowing up, getting huge. Compared to this little old plus 3, that's pretty insignificant. Whoops, that's my left hand touching the screen. So this is going to act like n factorial over 2n factorial. Now, as these get huge, they're still going to be the same thing, so they're going to cancel. And this thing is going to act like 1/2. So we're saying the limit as n goes to infinity of that nth term is going to 1/2. That's not 0. Therefore, the series will diverge by the nth term test. Okay? Now, in the next one, we have this summation k over natural log k. So again, that's the nth term. So if we take the limit as we can say k goes to infinity of this k over natural log of k, well, we know that, and this is like x over natural log x, the k is a higher order magnitude function than a logarithm, and so that is actually going to go to infinity. So again, by the nth term test, because that limit is not 0, we know the series diverges. Okay, yet another one. Okay, so here we are taking that limit as n go. We're going to again take the limit as n goes to infinity of our nth term, and hopefully we can see as n gets really, really big, that plus 3 and the plus 1 are each insignificant. That will act more and more like n over 3n, which is 1/3. Since that's not 0, the series diverges by the nth term test. Okay, so salt that one away because we're going to get many, many other ways of comparing series, but that one we don't want to forget. Okay, now we're going to talk about geometric series. These are really important. These are going to be building block series for us. So anything of the form a plus a times r plus a times r squared plus dot dot dot, the nth term is going to look like a times r to the n minus 1, and it's going to go on and on because it's infinite. And in summation notation, that's going to look like a times r to the n minus 1. That is, it's going to look like an exponential. Okay, so what we're doing is each time we're multiplying the next term by the same number each time. Those are what the characteristic of a geometric series. So you might say something like 1 plus 2. So I multiplied the 1 by 2, multiply the 2 by 2 is 4, multiply by 2 again, and so on. That is a geometric series. The a, the first term, is going to be the a, and the number that we're multiplying by each time is the r. And in a geometric series, you can always find those if you divide successive terms. So if you take ar to the second divided by ar, you're going to get r. And if you take ar divided by the a, you're going to get r. And so that's a characteristic of geometric series. Now, what we find out is that this series, this infinite series, is going to converge to this sum. So this is unusual. It's very rare that we can not only tell that a series converges, but what it actually converges to, what that sum is actually going to be. Now, it only converges when our common ratio, r, is between -1 and 1, and it will diverge everywhere else. So this absolute value of r less than 1 is the equivalent to saying -1 less than r less than +1. That is known as the interval of convergence, which we will be talking about a lot down the road here. And so we'll talk about it so much that we're going to agree that we can abbreviate it as an IOC. That stands for interval of convergence. So where does this formula come from? This fact that an infinite geometric series, a plus a times r plus ar to the second, on and on and on, actually is going to equal this sum, a over 1 minus r, as long as our r cooperates by being between -1 and 1. Well, let's explore that. This is actually a proof of that. So here is how we do our finite geometric series. So S of n is going to be a plus a times r plus ar squared all the way out to the nth term. Now, if we multiply that same thing by r, then what we get is the a is going to get multiplied by r. I'm going to write it underneath the other ar. This gets multiplied by r and becomes ar to the second. And we keep doing that. The second to last term is going to be this one. And when we multiply our last term, ar to the n minus 1 times r again, we'll get a last term of ar to the n. Does that make sense? Now, these all line up next to each other because what we want to do is subtract those. And when we do, the a comes down through unscathed, but all of these are going to cancel each other. It's called a telescoping series when they all collapse like that, except for our very last one. So that comes through as a minus ar to the n. Now, on the left side, we have s sub n minus r s sub n. So on the left side, we'll factor out that s sub n, leaving the 1 minus r, and then we will divide that over. So we're going to get s sub n is a minus ar to the n all over 1 minus r. Now this is a finite sum right there, so we say, well, what happens if we take the limit as n goes to infinity? Well, the a is a finite number, the r is a finite number. The only thing that's really of interest is what is going to happen to this a times r to the n. Well, it turns out if r is in between -1 and 1, which is the same thing as saying the absolute value of r is less than 1, every time you multiply it by itself, it's going to get a little bit smaller. So think like 3/4, or 3/4 times 3/4 is going to be 9/16. Well, 9/16 is less than 3/4 because if you multiply top and bottom by 4, you know that 3/4 is the same thing as 12/16. So it gets a little bit smaller. It's 3/4 of the original 3/4. And you just keep doing that over and over again. That is going to go to 0. And what we're going to get is exactly our sum, a over 1 minus r. If that r is greater than or equal to 1, then that is going to blow up and go to infinity. Well, if it's 1, yeah, that's a different issue, but it won't converge because, well, if it's bigger than 1, let's deal with that first. If r is bigger than 1, then each time you multiply it by itself, it gets bigger still. And so if the absolute value of r is greater than 1, then r to the n, as n goes to infinity, is going to blow up and go to infinity. If r is 1, we're going to get, so if r is 1, we get a minus 1 to the n is just going to be a over 1 minus 1. We get 0 over 0. And what are we going to do with that? Not totally clear. But if you think about it, if r is 1, that means we're going to take a, because each time we multiply by r, we're getting the same thing, and that's going to blow up and go to infinity. And if r is -1, we're going to get a minus a plus a minus a, and we've talked about that before. In the case of 1 minus 1 plus 1 minus 1, that's going to diverge as well. So at the end of the day, this is what we get. This is our sum, and we need to know that from memory, and we need to know what values of r will make that converge. So let's do some examples here. So here are some series. So can you, first of all, recognize these are actually going to be geometric? And if you're not, write out the first few terms. So let me switch to white there. So if we plug in 1 for k, we're going to get 1 minus 1 is 0, 1/2 to the 0 is 1, so our first term is going to be 3. When we let k be 2, 2 minus 1 is 1, 1/2 times 3 is going to be 3/2. And when we let k be 3, then we're going to get 1/2 squared, which is 1/4 times 3, and you can see we're going to be multiplying by 1/2 each time. So the key is just, can you recognize, and it's even better if you can see it in this form, that anything that is going to be of the form, where's our summation written for that? Somewhere up here. So anything that's going to be in this form, a times r to the n minus 1, which is what we're seeing here. This is going to be the a, and the thing that's being raised to the power is the r. So our r is 1/2, and because the absolute value, because 1/2 is in fact in between -1 and 1, it will converge. And it's going to converge to a over 1 minus r. That's going to be our sum. And so if you know the a, when you put our first number we plugged in is going to give us that 3. That's the a, and 1 minus 1/2 is going to be 3 over 1/2, which is going to be 6. So believe it or not, those things eventually are just going to get closer and closer to 6. Okay, looking at the next one, can you hopefully see that what we're multiplying by each time is, oops, I bumped it again and shut it down. So our common ratio is -1/2. If you can't see it, you can just look at, say, a few terms. So if you take a -1/2 divided by 1, that's going to be -1/2. If you take 1/4 divided by -1/2, that 2 is going to be -1/2, and so on. So we can see our first term is a is the 1. Our common ratio is a -1/2. That is in our interval of convergence. So we know it is going to converge. And because it is geometric, we know furthermore it will converge to a over 1 minus r. That's going to be our 1 over 1 minus a -1/2. That's 1 over 3/2, which is 2/3. Okay, so the next one, can you recognize that as being geometric? If not, then we need to write out a few terms. So did I get my green pen up here? So what we can do is when you plug in 0, we'll get anything to the 0 is 1, plus 3/5 plus 3/5 squared, plus 3/5 cubed, and on and on and on. So it is going to be geometric. Our a is 1, our r is 3/5, and because our 3/5 is indeed less than 1, we know it will converge. And because it's geometric, we know it's going to converge to a over 1 minus r. That's going to be 1 over 1 minus 3/5, which is 1 over 2/5, which is going to be 5/2 or 2.5 or 2.5. Okay, next one, kind of crazy looking. Pi over 2 plus pi squared over 4. Can you see that our common ratio here is going to be pi over 2 because we're multiplying by pi over 2 each time? But we know that pi is approximately 3.14, so that makes pi over 2 greater than 1. So that means our r is not less than 1. In fact, it is greater than 1. So that means it's going to diverge. Okay, now that was a quick one. So on the next one, we can see when you plug in 0, our first term is going to be 2. Our common ratio is going to be 3/4. And because our 3/4 is less than 1, that means it is going to converge. Since it is geometric, we know it will converge to a over 1 minus r, and that's going to be 2 over 1 minus 3/4. That's 2 over 1/4, which is 8. So that is going to add up to be 8. All right, now is where we're going to talk about some stuff that's pretty deep here. So we've talked about this whole geometric series thing, and we know that, at least with numbers, when we go a plus ar plus on and on, that given that the r is less than 1 in absolute value, that will sum to a over 1 minus r. And we talked about that thinking that it was numbers, but we can also do that with variables, and that's what we have done here. If we choose our r to be an x and our a to be 1, you can see that we're going to get 1 plus x, because we're multiplying by that r, which is x, and then times x gives us an x squared, on and on and on. Now, according to what we've said, this has to converge to a over 1 minus x. That's our r there, and our a here was a 1, so that's going to be 1 over 1 minus x. That is as long as r is less than 1 with the r in absolute value, which means that this is going to be true as long as the absolute value of x is less than 1, which is the same thing as saying that x is between negative 1 and 1. Think about this. We have on the left a polynomial with an infinite number of terms that is representing a function, but it's only equal to that function on a domain. Well, the function itself is actually defined for everywhere except for 1, but our approximation, our polynomial, is only valid between negative 1 and 1. The sequence of partial sums will converge to that, so the more terms we include, the better our approximation. So this now, we're in uncharted territory. This is really getting to what we want to do in this chapter. This sum, n going from 0 to infinity of x of n, is like a polynomial, but polynomials don't have infinite degrees, and they don't diverge for the wrong choices of x. Just as infinite series are more than just sums, infinite series of powers of x are not just a polynomial. Now, this is, I think, pretty powerful. I really encourage you to do this. On your calculator, put in y1 equals 1 over 1 minus x. For y2, let's write out our series, our infinite series, just out for the first 10 terms, or 11 terms, I guess. So you're just going to put in for y2, 1 plus x squared, all the way out to x to the 10th. It's a little bit tedious, but try it. Choose a window on your graphing calculator that has, say, an x-min negative 2 to 4, and an x-min and x-max going negative 2 to 4, and a y-min and a y-max going negative 2 to 6. On your y2, if you left arrow off past the y2 and hit enter until you get that thick bar, then it will kind of look it'll be a little easier to see. Then you'll see something remarkable. When you hit graph, then the first thing you're going to see is what I have drawn here in blue. That's our function y equals 1 over 1 minus x. Then you'll see chugging along your thick line is our 10th degree polynomial approximation, which you'll see is not even close out here because we're outside of negative 1 to positive 1. But once we get close to just past negative 1, it's going to really be remarkably close. That's why you need this thick line, because it's going to almost be a perfect fit for that original y equals 1 over 1 minus x until you get to that boundary of 1. And then if you go up far enough, they'll start to separate. And the further you go, it separates even more, because you can see the curve is really down here now, and ours is still the red. So this is pretty remarkable, but you can see just how amazingly well that polynomial approximates that function on that interval of convergence. So we need a bunch of vocabulary here. An expression of the form, the sum of the c sub n x sub n's, that is, when we expand it out, c sub 0 plus c sub 1x plus c sub 2x squared, on and on and on, that's just a number times the power of x, is known as a power series centered at x equals 0. If you write in the yellow here, this sum c sub n times x minus a to the n, then you get a polynomial where all of the powers are x minus a's instead of the x's. So you can correctly think of that as being x minus 0, and this as then being x minus something other than 0. So this then is a power series centered at x equals a. So it's really easy to see what the center of a series is. If all you see is powers of x, that's centered at 0. Otherwise, you're going to see, if these were all like x minus 2's, that would be centered at 2. If these were all x plus 3's, that would be centered at negative 3. Now, the term c sub n x minus a to the n is called the nth term, and again, a is the center of the series. Okay, so those are power series because they have powers of x. So our original geometric series here, we're going to use as a building block. So that series is centered at x equals 0, and it's going to converge between negative 1 and 1. So this idea that this interval of convergence is typical. That is, a power series is either going to converge for all x, so we would say then it's going to converge for negative infinity less than x less than infinity. We'll think of that as centered then at wherever we want it to be, whatever the a is. Or it could converge maybe at some centered at the a. So it might be that it's going to be from maybe, say, like a plus 5 to a minus 5. Something like that would be an interval of convergence. But it's going to be symmetric around whatever the center is, whatever that, in this case, the a. Or it's going to converge only at the center itself. That is, it will converge for x equals a and diverge everywhere else, which isn't terribly interesting, but can happen. Okay, so let's see how we can create more power series using our building block series. So this we are going to come to over and over and over again. Okay, so we know that this series converges, so we can do some kind of surprising, maybe, I don't know, because we've not done this before, different kinds of algebraic contortions with this to create new power series that converge. So one is, if we replace that x in our known convergent series with a negative x, then we would say that this 1 over 1 minus the negative x is going to be our 1 plus x, and that means our series, where we're going to substitute a negative x in everywhere we see that x, will be 1 plus negative x plus the negative x squared plus the negative x cubed, on and on and on, which of course every time we get an odd power is going to be a negative, but every time we have an even power is going to be a positive again. So you get what we will call this alternating series, and we can say that's going to be a negative x to the n, if you like, is going to be that nth term. Okay? All right, now we can then doctor that up. So now we have this geometric series, this infinite series for our 1 over 1 plus x. It's this alternating series. If we in turn multiply this by x, then we get on the right side x over 1 minus x. So if we then take this that we've used as our series for 1 over 1 plus x and multiply through by x, it becomes x minus x squared plus x cubed minus x to the fourth, and on and on and on. I think I left off the 3 on that one somehow. Okay, so there we've created a new infinite power series for a new function, x over 1 minus x. Now we can find a series for this. So we start with our building block function. Remember, 1 plus x squared plus on and on is equal to 1 over 1 minus x. So if we replace this x by a 2x, then this left side would become exactly what we have here, 1 over 1 minus 2x. So if we replace every x in our infinite series with a 2x, then we should get equivalence. So I'm going to do that. And we could either leave it like that, or if you like, that would be 1 plus 2x plus 4x squared plus 8x cubed plus, and we could say that nth term we could write either as 2x to the n or as 2 to the n x to the n. Either of those would be great. Okay? All right. Now, the next one is kind of tricky. How do we get from our 1 over 1 minus x that we know is going to be 1 plus x squared plus x cubed, on and on and on. How can we make that look like a 1 over x? So here's your challenge. So if we think of this as being 1 over, and then go 1 minus x, do you see how when you distribute that, they're going to be equal to each other? So we can go to our series here, and where we see the x, we'll replace that by a 1 minus x. So that's going to become 1 plus 1 minus x plus 1 minus x squared plus 1 minus x cubed, on and on and on. Does that make sense? So you can see now, because of these powers, that this is going to be centered at whatever makes that equal to 0, at x equals 1. Kind of crazy? We will be doing more of this kind of thing. This is kind of a beginning. Okay, that will be where we wrap this one up.